All right. Okay, I think we are ready now. So, in new chapter, chapter 7, rotational motion and gravitation. Probably will not be able to do much about this. There it is in this chapter. Let's see the content. We will start with defining velocity like we did in chapter 2, but angular velocity. So rotational motion, what changes? Something is rotating in the same place, fixed axis. So it is not going anywhere. X is not going to change. Y is not going to change. What is going to change is the angle of rotation. So angular velocity. Then we will define the acceleration, angular acceleration. Then like in chapter 2, when the acceleration is constant, here the angular acceleration is constant, we can use those equations, the equations of kinematics, v equal to v0 plus at. We will have similar thing in rotational motion as well. Then in rotational motion, in addition to looking at the angular velocity, we also have to look at what is called tangential velocity, because every point, say imagine a disk is rotating, every point in the disk will also have some linear velocity. The point will be going around. So we have to talk about that as well. So we have what is called tangential velocity, then the tangential acceleration, and also something called centripetal acceleration. We will see what they mean. Then number 4, we'll bring in the Newton's second law, the dynamics for rotational motion. So we will apply the Newton's second law for the circular motion, something that goes in a circle. Right. Number 5 is omitted. We probably not have time to do that. Why do we study rotational motion? It is something important. It's an important part of everyday life. You know, the planets, including the Earth, go round and round around the sun. And also the Earth itself is spinning. So rotational motion is something very important. Wheels of the car and a bicycle tire, they all rotational motion. So rotational motion is something that we have to take seriously. The angular motion is expressed in terms of angular velocity, speeds, angular acceleration, and centripetal acceleration. So we will see what they mean, but here's an overview. Gravity also part of this chapter, because we are going to apply the rotational motion combined with Newton's law of universal gravity and the Newton's laws of motion. We can explain space travel, satellite motion. These are very important, of course. If not for the satellite that is in the orbit, there are thousands of satellites, we will not have the GPS and so on. So it's very, very, very technologically important topic. This person, whose name is Kepler, he had 3 laws for the planetary motion, and before Newton, okay? But when Newton came, he used his laws, the Newton's 3 laws, and he was able to derive these 3 laws theoretically from his Newton's laws. Okay, right. In angular motion, it's very simple because we already know the concept. We know what velocity is, what acceleration is, and displacement, and so on. All that happens now is x, which is the position, will be replaced by angular position. So we say that is angular position. So that means displacement, which is delta x, will be replaced by angular displacement. That's all, So once you understand what these theta, delta theta, and so on, we will automatically have all the equations we need, which we have learned already. And velocity, this is the normal velocity, the linear velocity, will be replaced by what is called angular velocity. The symbol we use for angular velocity is this letter omega, okay, Greek letter omega. And acceleration, the linear acceleration, will be replaced by alpha. Alpha is the angular acceleration. So everything has a corresponding rotational quantity. So we will teach ourselves what these things mean one by one. So let me start with this angle. Angle we measure in degrees, right? You know. So if you go one full cycle is 360 degrees. So you divide the one full circle into 360 division. One division is 1 degree. But that's not the SI unit for angle. The SI unit for angle is called the radian. You know that, right? Radian. How do you define the radian? Very simple. Yeah, in terms of the pi, right? So it's a definition is suppose you have an angle theta, probably let's say 30 degrees, say just given a particular number, say something like 30 degrees. What we do, we draw a circle and project that angle onto the circle, and this is arc from that angle, we call it arc, and measure the length of that arc, called S, divide by the radius of the circle that you are using. This ratio, the arc length divide by the radius of the circle, if you substitute those values and calculate it, whatever the number you get, that will be the angle in radian. That's how you define the radian. So you can see now 1 radian should be, the S must be equal to R, right? That is when S over R is equal to 1. 1 radian is going to be quite a big angle. It's probably something like 57. We can derive it. How do we get the relationship between degrees and radian? It's quite simple. Let's look at the theta 360. If it is 30, it is something like this much, right? So 90 is this is the arc. 180 is this whole thing. So 360 is the whole circumference. So if you want to get the angle 360 in radian, the S will be the circumference. You all agree with that? Circumference, because the arc will be the whole thing, circumference, divided by the radius. So if we can somehow get the radian for 360 degrees, that's our purpose. Let's do that. This is done by knowing about pi. What is pi? Pi tells you what is the ratio of the circumference to diameter. How many diameters you can place in the circumference. So that is the ratio, that ratio is called the pi. So in terms of the circumference, pi will be C divided by diameter will be 2 times R. Therefore, C will be 2 pi into R.
What's meaning diameter?
Diameter is 2 times the radius. You don't know the diameter? Yeah. You know, diameter is, see, if you have a circle, this is diameter. This is radius. You know the radius, right?
Yeah.
So the line that crosses the center, one end to the other end, is the diameter. Diameter is 2 times the radius, like R. Right. So now you have circumference will be 2 pi R. Now I'm going to go and put it in here. Circumference is 2 pi R. Divide by R. What do you get? 2 pi. So 360 degrees is 2 pi radian. We proved it from the definition of the radian. Now we know that 360 degrees corresponds to 2 pi radian. Right. So now we can, for example, now we can calculate how much is 1 radian. So 1 radian, this is the conversion. 2 pi radian is 360 degrees. So radian cancel with radian, and 1 multiplied by 360 divided by 2 pi, you will get 1 radian as degrees. As I told you, it is quite a big angle. 1 radian is almost 60 degrees, right? Not 57.3 degrees approximately. Do you need to memorize it? No, not really. You don't have to. But this one you have to memorize. Well, instead of saying 360 equal to 2 pi, I can say it's better. easier to say 180 degrees is equal to pi. Memorize this. This you should know. Okay, we are not going to tell you that in the exam. It's something that you are supposed to memorize. Right. Then you can go on to say, suppose you have any angle theta in degrees. If you want to convert it into radian, all you have to do is to multiply by pi, divide by 180. What about the other way around? If radian is given, how do you get into degrees? You do multiply by 180 and divide by pi. You don't have to memorize that. You know the conversion factor. You learned in chapter 1, conversion of unit. Right, chapter 1. All right. Chapter 2 is the kinematics. Right. Now here we have a disk that is rotating. And you are looking at this point P in the disk. When the disk is rotating, let's say it's rotating counterclockwise, you need to understand these notations, okay? CCW mean counterclockwise. That means rotating opposite to the clock hand direction, counterclockwise. CW mean clockwise, okay? So please remember them. CCW mean counterclockwise, CW mean clockwise. Okay. Yeah, we'll come to that. Okay, so let's go slowly. So this is rotating, and we have a reference line which is not rotating. It's a horizontal line like the x-axis, for example. And now I will say this point, its angular position of this point, we draw a line from the center to that point, is the angle this line makes with the reference line. So theta initially 0. Because now it's moving, the P is going to rotate. So initial angular position of the point P is 0. So, there is no x, right? It is not going anywhere. It is only the angle that is going to change. It will be just keep rotating. Then, after some time, the point comes here. Now the angle changed. So theta final is some theta. So this is called angular position. Now you understand the meaning of angular position. Like position x, we can, for rotational motion about a fixed axis, okay, it is not going anywhere. So we have angular position. Okay, angular position. So right, first thing. Once you have the angular position, now I can get the angular displacement. All right, before that, we have to talk about rigid body. What do you mean by rigid body? Because these rotational mechanics, we will do for rigid body first. We cannot do this for liquid. Liquid is not a rigid body, it's flowing. Air, fluid, gas, liquid, we cannot apply this mechanics that we are learning. We can only apply for rigid body. What we mean by any solid is, in general, rigid body. Rigid body means each part of the body is fixed in position relative to all the other parts. That's what the proper definition of a rigid body. For example, jelly. If you check jelly, it's a solid, right? But it's not a rigid body. It is wobbling, right? So the relative position can change. If this is the distance between these 2 points is say 1 centimeter, after a while it can become 2 centimeters. It can wobble and the shape can change. So that is not a rigid body. So now you understand rigid body. The reason I told you about rigid body is whatever we do now is valid for rigid body only. So when the rigid body, for example, if you have a rigid body, if it is rotating about a fixed axis, every point will cover the same angle, right? So point P and point Q. If this is rotating, say, about 30 degrees, this guy will also rotate the same amount. So that is one thing that we need to remember. All parts of the object of a body rotate through the same angle during the same time if it is a rigid body. So we have again a disk. So let's say at certain time t initial, the point A is here and it is the angular position is theta I. Later this moves and comes to this point, then its angular position has changed to theta final. Then we say the angular displacement is equal to theta final minus theta initial. Like delta x is x final minus x initial. Here angular displacement will be final angular position minus initial angular position. So I can take an example if you want. Let's say theta initial is 30 degrees and theta final is say 55 degrees. Delta theta will be this guy. Oops, what did I do? Delta theta will be, if I use another color, will be this guy, right? This will be the delta theta. That will be 55 minus 30. Whatever it is, 25. So that's very clear. Right? So let's move on. So we know what angular position is. Now we also know what angular displacement is. What is next? Velocity, right? That's the order we did in chapter 2 also. We define the position, then we define the displacement, then we go on to define the velocity. Now here it is angular velocity. If you remember our definition of velocity, the average velocity is delta x displacement divided by time. We do exactly the same thing. The average angular velocity will be displacement divided by time, but not the delta x, not the ordinary linear displacement, but angular displacement. Done. So what about this letter omega? I told you that before, right? This is Greek letter. We call it omega. Maybe somebody might say, no, this is omega. Yeah. No, Om is the somebody's name, okay? But the Greek, this is the omega. It's actually omega. This is also omega. What's the difference? This is the small omega. This is the capital omega. This is the simple omega. This is the capital. Like in English, they have capital letters, small letters. So this is the, we use the small omega for angular velocity. Good. What's this? It is repeating me. Okay. Come on. I need to change the color of my. Okay, come on. The AI is. How do I do now? Yeah, okay, fine. Let it do it. Let's continue. I want to change the color of my pen. Wow. Never mind. Let me keep. Oh, right, here it is. I'll take this caption out. Yeah, good. Right, here we are. So average velocity is, oh, I moved to the other slide. Right, this is where we were. It's clear. Let's go to the next slide. I'm sorry? Okay, so angular velocity, we define the average angular velocity. If you remember in chapter 2, what we did next is to talk about instantaneous velocity, because that was average velocity. So simply the same way, instantaneous angular velocity will be the limit of the average velocity as the time interval approaches 0, in the same way. What about the unit? So it is angular position divided by time. Angular position is radian and the time is second. So it will be radian per second. By the way, how do you write the radian? Do we put R? No. Do you put RADIAN? No. We only put RAD. That's it. Okay. So actually radian has no dimension because it's a ratio of two lengths, right? S divided by R. So it's a dimensionless unit quantity. Now comes what you're talking about. So rotation about a fixed axis is like moving for a linear motion, moving in a line, straight line. You have a positive direction and a negative direction. So one dimensional, right? Similarly, when something is rotating about a fixed axis, it has two directions, like one dimensional rotational motion. Counterclockwise is one direction, clockwise is the other direction. So counterclockwise we say positive direction, clockwise we call it negative direction. Please remember that, okay? So do not change that. Counterclockwise positive, CW is negative. The long one is positive, smaller one is negative. Maybe you have to associate something like that to remember. Fine. Velocity will be positive if the rotation is counterclockwise. Velocity will be negative if the rotation is counterclockwise. But we will give the proper direction later. But for the time being, counterclockwise is a direction. It's not actually direction, right? It's keep rotating. But for the time being, let's assume that counterclockwise is the positive direction, clockwise is the negative direction. Now, if the angular velocity is constant, there is no difference between instantaneous value and the average value, because over a period of time, if it is the same velocity, I mean, it is the average velocity, it is also the velocity at each point in time. So, okay, naturally, the next will be acceleration. So we told about the position, then how the position is changing, that is velocity, then how the velocity is changing is the acceleration. So in chapter 2, we said acceleration is how fast the velocity is changing, the rate of change of velocity. Change in velocity divided by time. So similarly, angular acceleration, now look, this is not A, right? It is alpha. Greek letter alpha. So the average angular acceleration is again change in the velocity divided by time, but the velocity is not the linear velocity but the angular velocity. What about the unit? Angular velocity is radian per second, and per second, so it will be radian per second squared. Instead of meter per second squared, we have radian per second squared. Okay, we are repeating it here. Right. Okay, so what about the direction for acceleration? Well, if the acceleration is counterclockwise, it is positive acceleration. If it is clockwise, it is negative acceleration. But about the acceleration, we need to talk about it more seriously, but not in this slide. I will do it later, okay? Because acceleration direction not necessarily the same as the direction of the velocity. We talked about this before when you talk about the elevator. If the elevator is going up with the increasing speed, acceleration is also same direction if it is the increasing speed. But if the elevator is going up with the decreasing speed, although it is going up, acceleration direction is not in the velocity direction, it will be in the opposite direction. We have the same thing here, but I will demonstrate it better, with some simulation, but not here. We will discuss it in the next slide probably. I don't remember. When a rigid object rotates about a fixed axis, every portion of the object has the same angular velocity and the same angular acceleration. So that is the same, I have to stress that. Right? So angular velocity of every point is the same. Similarly, angular acceleration at every point in that object which is rotating about a fixed point is the same. But we will have something called tangential speed and tangential acceleration, but they will not be the same, but we still did not define them, so we need to wait to know what it is about. Angular acceleration, finally. What about the instantaneous value for angular acceleration? We just talked about the average value. Instantaneous value in the same way, defined as the limit of the average value as the time interval approaches 0. Right. Now, yes, I'm recording it, but anyway, we go on. Right. Now, what about, shall I? what about in general? This is a very nice. So we said before, if we have a disk like this, if the disk is rotating counterclockwise, right? We said, if a disk is rotating counterclockwise, we said the direction of this angular velocity is positive. Direction means we should be able to point it, right? This direction, so on. If something is rotating the disk, what do you mean by direction? It doesn't make sense. Okay? So we have a trick. We take your right hand, not left hand, it's very important, and curl your, not the thumb, except the thumb, in the direction of the rotation, and look at the thumb. Thumb is sticking out. It is out of the page. So the omega for this, when it is going counterclockwise, the direction of the omega is out of the board. So this is the direction. And we call it is positive. Okay? Coming out is positive. If it is rotating clockwise, on the other hand, then can I curl it like this? No, because it's rotating this way. So I have to flip my hand. So I can curl it in the same direction as the rotation. Now what is the thumb is pointing to? Inside. So, right, negative. So positive direction is out of the page or out of the plane or the screen, and negative direction is into the page. Please remember now, okay? So now we were able to give us, come to the front please. Here. You could have just sat there quietly. No, you did that and you caught. Come and sit here, please. So its direction is, when it is counterclockwise, it is out of the page. So it's positive. So we have a direction for that omega. Now it is in this plane, right? What if something is rotating out of the plane, like say what you see in this picture? So the way to get the direction is very simple. You take the right hand again. Suppose this is the disk that is rotating like that. So you can see, you grab the axle. Also, you should be able to curl your fingers in the direction of the rotation of the disk, and your thumb is pointing like that. What if it is rotating like this? Then if you keep like that, can you curl your finger in the same direction? No, you have to go like this. Then it will be in the other direction. So it doesn't have to be the same plane as your paper. Okay, it could be any plane. So in general, you should be able to give the direction of the omega in this manner. So you can read this. Grasp the axis of rotation with your right hand. It's very important. It must be right hand. If you use the left hand, everything will be opposite. So wrap your fingers in the direction of the rotation. That is important. You have to wrap in the direction of. So if it is rotating like this, you have to wrap like this. But if it is rotating like this, you have to wrap like this. So then look at the thumb. The thumb points in the direction of omega. So here again we are looking at the disk that is rotating, but this time it is rotating in a horizontal plane. So looking from above, the one on top A, it is rotating, looking from above, it is rotating counterclockwise, and you curl your fingers in the same direction, and the thumb is pointing up. So omega direction for this rotating disk is up, and this one, it is down. So that's very, very clear. So it's a vector. Angular velocity is a vector. It has a definite direction. Not only size, it also has the. Yeah, but for us, because we limit to fixed axis rotation. So it is like one-dimensional motion. We only have to worry about no x component, y component, because then it becomes, if the wheel is rotating disk is rolling, the axis is also moving, right? But here we have fixed axis. So we will limit ourselves to one-dimensional rotational motion. So we have only two directions, clockwise, positive, clockwise, negative. Not because we have, but it's become complicated, more difficult, so we don't want. We just stick to one-dimensional, fixed axis rotation. All right, now come the acceleration direction. Okay. Velocity direction is fine. What about the acceleration direction? To demonstrate that, let me go to this simulation. Right. Let's say we have this thing. This is the disk, this is rotating like that. Now tell me, what is the direction of the angular velocity? Positive. Or direction will be, yeah, I mean pointing out of the board. Okay. So let's say if this is the angular velocity. So because I'm moving counterclockwise, the direction will be positive out of the board, or counterclockwise if you want. You can say it in three different ways: counterclockwise, positive, out of the CCW, out of the board. Right. Now, what about the acceleration? Now let me say I am moving it with a constant angular velocity. What is that? 0. Can you talk about the direction when it is 0? No. 0 means 0. It has no direction. Okay, right. Now let me do this. I start with a small speed, but I can slowly increase the speed. Now there is acceleration, right? Increasing speed. So acceleration direction will also be the same direction as the angular velocity. Because I went like this, with the slowly, then I will increase and increase, and so I know my acceleration is in the same direction as the angular velocity, because I have an increase in speed, like the elevator problem. Okay, so acceleration is tricky. Now let me do this. Now it is going fast, then I slow down. What is the direction of the angular velocity? Angular velocity. Angular velocity is counterclockwise. Okay. Now I didn't ask acceleration. Listen to what I'm saying. Okay. Angular velocity is counterclockwise, but the angular acceleration is not counterclockwise. Why? It is opposite, because the speed was decreasing. So angular acceleration is clockwise, negative. Okay. And I can do like this now. I am going clockwise, right? What is the angular velocity? Direction? Negative. But if I slow down, what is the angular, not the velocity. Velocity is still negative. Acceleration is positive if it is slowing down. Same idea that you have for the one-dimensional acceleration direction. Right. So we can continue now. So let me read this. Now we are putting it in a different way. If we see that acceleration and the velocity are in the same direction, what is our conclusion? Speed is increasing. If the acceleration and the velocity are in the opposite direction, we know speed is decreasing. Right, now comes our equations. Remember this? Chapter 2, kinematics. So we are going to just borrow from chapter 2 and bring it to chapter 7. We say these equations are when the acceleration is constant, right? Similarly, if the angular acceleration is also constant, we can use the same analogous equation. All we do is replace the linear quantities by angular quantities. V will become omega, V initial become, that is the final, right? V final become omega final, V initial become omega initial, A become alpha, T is T, right? There's no angular time and linear time. The same thing. So we just borrow everything from chapter 2. There is nothing new here. Now we can even do questions. Here we have an example question. Let's look at this question. A wheel rotates with a constant angular acceleration. So you know what this is. This is alpha, right? So we identified our alpha. And it is constant. That means I can apply the equations of kinematics. And at t equal to 0, it has this velocity. So this is omega 0. Yeah, that is what you use, right? Not I, omega 0. So we got the omega 0. and we also got alpha. We know alpha and we know initial velocity. And in A, he is giving one more thing. He is giving the time t equal to 0 to t equal to 2 seconds. And he is asking during that time what is the angle it is rotating. That means he is asking for the displacement, delta theta. Right. So the way we do this question is we list the thing, right? In chapter 2 we say delta x, and we say initial velocity, and we say final velocity, and we say acceleration, and we ask for the time. The same way now we will, instead of linear displacement, we will ask for the angular displacement. Instead of normal velocity, we will ask for the angular velocity, initial, angular velocity, final. Instead of A, I will ask for the alpha and the time. That's it. Is this given? That is the question. That is the question. He is asking for delta theta. Is this given? Yes, 2 radian per second. Is this given? No. No problem. And this is given 3.5. And this is given 2. 2 minus 2, 0 is 2. 3 given thing, only 2 unknowns. That means I can find both of them. Which equation should I apply? The equation that doesn't have, I'm not interested in the final velocity, right? So I have to look for the equation that doesn't have the final velocity, namely this equation. Substitute and get the answer. Omega 0 is 2, t is 2, plus half, A is 3.5, and t is again 2 square. When you do the calculation, you will get 11 radian. Not meters, but radian. Done. Simple as that. Okay, so this is why when I say in the final exam, there is no chapter 2. Why? Chapter 2 is here in chapter 7. So I don't need to test you chapter 2 again. And you can do B and C, but I will not do. Please do it on your own. We will continue. Tangential velocity and tangential acceleration. What is tangential velocity and tangential acceleration? Let me explain with this object. This is a rigid object which is rotating about a fixed point at the point O. And let me look at this point in that rigid object, the point P. So when this is rotating, every point will be rotating with the same angular velocity. If I take another point P, it will also will be rotating, but it will be at a different distance from the origin. Let me call it R dash. If I ask you, P and Q, do they have the same angular velocity? The answer is yes. P and Q, do they have the same angular acceleration? Again, yes. Right? They have the same angular acceleration. My target is now to talk about this velocity, the linear velocity. See, the red arrow is showing the velocity. This guy, at the same time it is having angular velocity, it will also have a linear velocity. It will be moving at this point. It is going in a circular path, but at this point it has a velocity which is tangential to this, its path, or perpendicular to the radius. This is the tangential velocity of the point P. Now we can get a relationship between this tangential velocity or the linear velocity of this point and the omega of the whole object. How? We will start with the definition of theta. Theta in radian is equal to the arc length divided by the radius. That is how we define the delta theta in radian. Let us divide both sides by delta t. If you have an equation, if you do the same operation both sides, we are not changing the equation. Now what is this? This is omega by definition. And what is this? This is the tangential velocity by definition, the linear velocity. So now we get an equation that connects the angular velocity to the tangential velocity through this equation. I can call it Vt to say that is the tangential velocity. Now, if I rewrite it, I can say the tangential velocity is equal to r into omega. P and Q have the same omega, true. But the linear velocity of this, if I call it V dash, is not the same as the V. Because tangential velocity is r multiplied by omega. So for the P, r is small. For Q, r is big. So as you go away from the axis of rotation, you will have a bigger velocity. Maybe if you have ridden go on a merry-go-round, you know what a merry-go-round is, right? A horizontal platform where small children play, rotating platform, merry-go-round. So if you are near the axis, you are moving slowly. If you are near the rim, you are moving faster. So you can explain using this equation, because the tangential speed is what you feel as the speed. Both of them, the person here and the person here, will have the same omega, but they will have different tangential velocity. The further away from you from the axis of rotation, the greater will be the tangential velocity. Tangential velocity, so here we put it nicely. Tangential velocity equals distance from the axis of rotation times the omega angular velocity. Now we can go to the next step. If something has a angular acceleration, then it will also have a tangential acceleration. Angular acceleration means the omega is changing. So we start with Vt is equal to r omega. Then when it is changes, omega changes, delta V also will change. Now you define both sides by delta t. And now you recognize this to be the angular acceleration and this to be the, you recognize this to be the tangential acceleration and this to be the angular acceleration. So now we have a similar relation between the accelerations. Tangential acceleration is equal to r, the distance to the axis of rotation, multiplied by angular acceleration. Tangential acceleration equals distance from the axis of rotation times the angular acceleration. So we got now centripetal acceleration. What is centripetal acceleration? Imagine a car going in a circle. And it has the same speed. Let's say the speed is 60 kilometers per hour. And it is here, again, it is 60 kilometers per hour. So this speed is like this, let me call it V1. Here, the velocity direction will be like this, let me call it V2. Can I say velocity V1 is equal to velocity V2? So the car has a speed of 60 kilometers per hour, and in this direction, here again, it is moving the same speed around this circle. Here again, it has a speed of 60 kilometers per hour. It's constant speed. Now my question is, can I say it is constant velocity? Constant speed? Yes. But is it constant velocity? No. Why? No. Why do you say it is not constant velocity? The velocity V1 is not equal to velocity V2. Speed V1 is equal to, no. Speed V1 is equal to speed V2. But velocity V1 is not equal to velocity V2. Velocity means it has direction. If two velocity to be equal, they have to be equal in both magnitude as well as direction. So when the car is here, the magnitude is the same, but V1 has this direction, V2 has another direction. So the velocity is not the same. If velocity is not the same, it has acceleration, because change in the velocity divided by time is the acceleration. So there's a rate of change of velocity, that means there is acceleration, and one can actually prove the acceleration direction will be toward the center of the circle, wherever it is. At this point, it will have an acceleration like this. At this point, it will have an acceleration like this. At this point, acceleration like this, and so on. So, and we call it centripetal acceleration. When something goes in a circle, although magnitude is not changing, even if the magnitude is not changing, but the direction is changing. Because of the direction changing, it will have an acceleration, and this acceleration will be directed towards the center of the circle. So we call it centripetal acceleration. Centripetal means what? Centripetal means center seeking, petal. Seeking, looking for the center. So that is why the name centripetal acceleration. So here we have the same picture. One can actually prove the direction. See, the V initial, V final. They are not the same. Magnitude may be the same, but the direction is different. Because of the direction changing, it will have an acceleration to the center of the circle, and we call this as centripetal acceleration. And then we go to the next slide and we say, okay, I know the magnitude of that acceleration. We call it AC, C for the centripetal. And the magnitude of the centripetal acceleration is given by this expression, speed squared divided by the radius of that circle. So here we need to remember two things, right? There is something called centripetal acceleration, because the direction of the velocity is changing, and the direction of the centripetal acceleration is toward the center of the circle, and the magnitude of the centripetal acceleration is speed squared divided by the radius of the circle. Now, I can substitute for this in terms of the omega, because we know the tangential velocity will be equal to r omega. So r squared omega squared, one r cancel with an r here. We get another alternative expression for the centripetal acceleration. Now this time in terms of the angular velocity. This is also correct as this one. They are both give the same centripetal acceleration. The first one here, the one up there is in terms of the angular velocity. The other one is in terms of the speed, tangential velocity. Right. Now we go to, again, something moving in a circle. If the speed is changing, there will be angular acceleration. Angular velocity changing means there will be angular acceleration. If there is angular acceleration, we will have a tangential acceleration as well. Here. So angular acceleration multiplied by the radius will be tangential acceleration. So something goes in a circle with the changing angular velocity, that will result in angular acceleration. Therefore, we'll have a tangential acceleration as well. So this point we'll have two acceleration. One is the red arrow, the tangential acceleration, and the green arrow, the centripetal acceleration. Centripetal acceleration will be toward the center, and the tangential acceleration will be perpendicular to that, because it will be tangent to the curve. That means it will make a 90 degrees angle with the centripetal acceleration direction. So total acceleration now, I will say, because they are in two different directions, the total acceleration A will be tangential acceleration vector plus the centripetal acceleration vector. You have to add vectorially. But this is easy to do. If someone asks you what is the total magnitude of the total acceleration, it will not be AT plus AC, but because they are perpendicular to each other, you can apply directly the Pythagoras theorem. It will be the component along the tangent squared plus the acceleration along the radius or direction or the centripetal acceleration toward the center squared, add them and take the square root, that will give you the total acceleration magnitude. Yeah, I want to finish it because I'm recording it. I don't want to stop in the middle. Now I can take the attendance. It is not recording? Good. It is recording, right? Yeah. How do I stop the recording? Never mind, let me stop sharing as long as recording it.